be swarms of physical or software agents that move on a network, like software agents that are used to optimize the way a computer network is used, or a swarm of robots that perform collectively some behavior. And in this case, the research goal is to model, design, and build and control such swarms. So here you see some example of natural swarms. Here you see a collection of ants transporting a stick in a coordinated way. They're doing something that they could not do alone, but there is nobody directing them. Here in the other two videos you see some ants that collaborate here to fill a gap between this stick that is in the vertical plane. We are here in the vertical plane. This is not working anymore. And here the researcher has broken this stick and they build a living repair so that other ants can use the stick again. But they can do even much bigger structures. You see thousands of ants that build a kind of bridge to pass over a pond that has been flooded. These are just a few examples. There are other examples like bird flocking or fish schools, where there are coordinated behaviors that emerge from the local interaction between many individuals. Okay, so the goal of research in swarm intelligence is to understand how the natural swarms function and to design and implement artificial swarms. And sometimes there are also hybrids. And there are, for example, studies that are trying to understand how robots can influence the behavior of natural swarms. So swarms of robots that interact with swarms of animals. So when we talk about swarm intelligence, we might distinguish between scientific and engineering threads of research. The scientific swarm intelligence is concerned with understanding natural swarms, while the engineering swarm intelligence is concerned with design and implementation of artificial swarm systems. And obviously the interaction between the two is that engineering swarm intelligence has historically taken inspiration from scientific swarm intelligence studies to design these algorithms, problem-solving devices. So the research method that has been historically used is that there are some biologists that observe a social behavior and build a simple model, or at least they build a model, they try to do it as simple as possible, to explain this behavior. Then there are other researchers, typically computer scientists, engineers, roboticists, researchers in operation research, that use a model of the social behavior as a source of inspiration for solving some real-world, some practical problems that have some analogies, some similarities with the behavior that is observed in the natural system. Okay, this is it's not a strict. First, it's no longer completely true that this is where we proceed, because the number of examples from nature, at least the most evident, most obvious example from nature have been used, so there are no more inspiration to be taken. And also because we found out that as engineers, there are many occasions in which we have swarms of agents that can be designed and can be put to work where there is really no need for a natural inspiration. Okay, so what I've listed here are some behaviors like foraging, division of labor, cemetery organization, self-assembly, cooperative transport, flushing synchronization, all behaviors that are studied in swarm intelligence by biologists and that have been at the basis of inspiration for some successful applications. So, for example, we have foraging that I used 20 years ago to design the ant colony optimization, which I will briefly overview in a moment. Then there are a number of other inspiration that have been used, for example, to design adaptive task allocation algorithm or for doing data clustering or for various implementation of robotics systems. So I will talk now a little bit about this, and then I will focus most of my presentation on this part that is my my main research interest in the last 10 years. So ant colony optimization was probably the first successful example of how you can translate some natural behavior from swarm intelligence to an application. So the idea was given by the work of biologists called Jean-Louis Delevoux, who proposed this experiment. There is a nest of ants here, down here, and the food source there. And the ants can reach the food source using this double bridge. And when they reach this decision point, they can choose whether to go left or right. These ants, which this experiment has been run, are basically blind. Okay, so they have no idea about the topology of the double bridge. So what they observed is that if you run experiments for a while, the ants end up finding the shortest path. And they do so, the explication that they give for this phenomenon is quite simple. The ants, when they walk, they deposit some pheromone on the ground, and when they have to decide where to go, they prefer, in probability, to choose a path where there is more pheromone. So when the ants arrive here at the very beginning, there is no pheromone in the system, so they choose randomly whether to go left or right, with approximately 50% of probability for each of the two choices. Then those ants that by chance decide to go this path, they will arrive here when those ants that have chosen this path arrive here, because of how the bridge split. And then they get some food, and when they go back, they arrive here again at the decision point, but now there's a bit more pheromone on this side than on the other. Okay? So you have a kind of positive feedback cycle, which makes the ants, after some time, use this shorter branch. So here, obviously, the ants are used. They are a swarm intelligence system. They are decentralized. They do not use any global information. There is no ant that is in charge. So you can remove any of the ants. The system continues to work as before. And they are doing some optimization. A kind of simple optimization for us humans, because we can solve this problem just by looking at it. But still, they're doing some optimization. So the idea was to use a similar mechanism to find shortest path on graphs. So a graph is a collection of nodes and edges, and I don't know if you can see here, it's a big thing. There are connections between the nodes. The connection can have different lengths. And the goal of the problem is to find the shortest path that connects one source to a particular destination. This particular problem is an easy problem, mathematically speaking, but it is representative of a whole class of mathematical problems that can be very difficult, for which we do not know how to find optimal solution in reasonable time. So the idea was to let, so an ant, the idea was to use artificial ants and to place them randomly on this graph, and an artificial ant can move or jump from one node to another using artificial pheromones. The artificial pheromones are numbers that are associated to the edges. And you can have many of these agents, these artificial ants that explore the graph, and they do search the graph, and then they update the artificial pheromone on the edges as a function of the quality of the solution they find. So if a ant, just to give an example, if an ant finds a very good path, which is a short one, the hand will put a lot of pheromone on the edges. If another hand, for example, does a path like this, which is much longer, it will put only a very small amount of pheromone on the edges. If you iterate this algorithm high number of times, you can prove that it's guaranteed to find the optimal solution on this type of simple problem. Okay, so the idea was, okay, the biologists proposed a model, as I said before. The biologists, they try to explain what they observe. So they proposed a model that says that the probability to choose one of the branches is proportional to some measures that is consistent with the idea that it is the pheromone. And then what we did was to use that model, you see this equation, to propose an equation that can be used by the artificial ants, an equation that is quite similar. Basically, if you remove this part, it's the same equation as there. Okay? And then we added this part that is some additional information that we can use because we are engineers, because we know the problem that we are solving. And that is necessary because the problems that we are solving are much more complex than the simple problem of selecting between two paths that is solved by the ants. Okay, so once you have the representation, that is this graph representation, and you have the mathematical rules to build a solution. So this, the straightforward is an equation that tells to artificial ants how to move. Basically, if you want to read it, the equation says that if a ant is in node I and wants to move to node J and its final destination is D, then it should choose among all the possibilities the one that has highest pheromone and highest some other information that we don't care about right now. And this is done probabilistically. So I was saying we have the representation, we have the rule for building a solution, and then we have a rule for updating the pheromones. And this rule for updating the pheromone, in this figure, says that the new value of the pheromones is the same as the previous one, minus some evaporation, plus some new value that is given by the answer they've used at the edges. Okay. Well, now we have the representation and the rules. We can write a program, a procedure that can be applied to solve this type of problem. And then once we have this procedure, we can, as I said, apply this kind of reasoning to a whole large class of problems that is called the class of NPR problems, that are problems that you find in everyday life, like scheduling problem, vehicle routing problem, timetabling problem, or problems that, well, everyday life in logistics or in companies. As a person, you probably can survive without, but if you work for a company, it's very useful to be able to solve these problems. And the way the algorithm is working is a stochastic algorithm. That means that it does not produce always the same solution, and is not producing the optimal solution. Well, it can, but it's not provable. And but it does so. Okay? So it gives you the possibility to generate in a reasonable or short amount of time a solution that is quite good. And the algorithm is good enough that we were able to start a company that is living by selling this type of technology. Okay, so this, so I'm still working on this stuff, but it's no longer, since 10 years, it's no longer my main interest. My main interest is drone robotics. So how to let a group of robots cooperate to achieve to perform some task or to achieve some goals in a decentralized way without having any robot that is in charge. Okay. So the swarm robotics research, the same is studies, it just embodies swarm intelligence. It studies how to design, build, and control swarms of cooperating robots. And The main characteristic is that robots are relatively simple and incapable. And they, as I said, they use only local information and communication. When I say that they are relatively simple and incapable, it means that they can be quite complex as a single robot, but they are simple when compared to the tasks they are given. So that means that the single robot cannot perform the task. They need to cooperate to be able to do something. So to give you an example of what type of things we do, these are robots that we built, and we are just here using them to grasp the child and pull the child on the ground. So here the robots have these grippers. The child was put some red bars in the trousers, and so that the robots can grab the child, and also the bar are emitting infrared so that the robots can see them. The robots attach to each other, they grasp each other, and when they are formed four structures that we call swarmbots, they can cooperatively pull the child. Okay, so, and we are still paying psychotherapy for the child, still recovering after 3 years. Okay, so what are the motivations? Why do we want to do research in robotics? There are a number of reasons. One is that I've summarized them under 4 terms: parallelism, scalability, fault tolerance, and cost. So the first is parallelism is because we have many different robots that can perform different tasks at the same time. Okay? So basically, you can throw a bunch of robots on the ground, and then they can work in parallel. We want systems that are scalable. That is, you add more robots, you get more work done. This is one of the reasons why we want to use local information, local communication, to avoid scalability problems, basically. The robotic system has higher probabilities to be fault tolerant because there is no central point that can break down. There is no single point of failure. If a robot breaks down, any other can take over. There is no particular robot that is more important that if it fails, does not, or the whole system does not work anymore. And also, the single agents are less prone to failure than a much more complex robot that could do the whole work alone. So you have to think that not always, but often, taking the small robotics approach is in competition with the approach of building a big, very complex, very powerful robot. So, and we don't know yet whether maybe that is the right way to do things. Research is an open question whether small robotics will end up providing some real-world useful applications or not. So these are the reasons why we believe that the small robotics approach is promising. And finally, the last reason why we think is the reasonable way to go is that simple robots are cheaper to build than complex robots. This is obvious, but we can usually the raising cost of an artifact is more than linear in the complexity of the artifact. So The hope is that to solve a problem with a big complex robots, you would need maybe 100 small robots, but these 100 small robots will be much less expensive than the big ones. Okay, so I have run two big, so I have coordinated two big European projects called SwarmBots and Swarmanoid that lasted approximately 80 years altogether. When I say big project, okay, the project of approximately 2.5 million each one, 2 million GBP, and that so involved 4 or 5 European labs and 20, 30 researchers. And the goal in both projects was to build proof of concepts that showed that it was possible to do this cooperation among the robots. In particular, we were studying not only logical cooperation, but also physical cooperation between the robots. And obviously, we were doing so using swarm intelligence principles of decentralization, local sensing, communication, self-organization. So the first of this project, SwarmBot, well, the first thing is what is a SwarmBot? A SwarmBot is an artifact, so it's a robot, that is composed by a number of smaller, simpler robots that are called S-bots, and that are capable of self-assembly, so attach and detach from each other. I have here okay, this is the S-bot. It has two grippers. Actually, then in the experiments, I'm only using this one because this gripper here tended to break very easily. And they have this ring around that can be used by other robots to grasp them. And they have a number of sensor actuators. For example, they have loudspeakers, they have infrared, they have a camera that is pointing to the ceiling. And then, yeah, what you see here is that a single robot is capable to lift another one. They are so big, approximately half a kilo. And they can move on moderately rough terrain. Okay? But as soon as terrain becomes more rough, they can still move by attaching to each other, as you can see in this other video. Okay, so for example, these three robots are attached to each other, and they manage to overcome this obstacle here by collaboration. Okay, so a SwarmBot is thought to be able to do tasks such as move a rough terrain where a single robot would get stuck, you've just seen, overcome obstacles that a single robot cannot overcome alone, as in the video that you just seen. Retrieve items are too heavy for a single robot, transport broken robot to repair centers, and so on. Okay. So here, so this we already seen. Here we have another example of a swarm that manages to climb a step. Okay, that one was abandoned because the strain in the gripper was becoming too strong, and there was a high risk to break the gripper. Breaking the gripper is 2 days' work to repair it. So there is a built-in mechanism that opens when the cycle is going to break. So what we did was to study a search and retrieval scenario in which a swarm of robots has to cooperate to search an object and to transport the object to a goal location. And this is the typical arena that we have given as a scenario to let all these people work together and the robots work together also. What you see here is the goal location here, typically in the form of a light. There is an object, you see here, it's a heavy object. You can make it of different weights so that you might need a different number of robots to transport it. There might be obstacles like walls or holes. And these are the robots. And the robots have this vision range. So the robots, as I said, they have to transport this object from its start location to the goal location. And to do so, they have to cooperate not only because the object is heavy, and this requires more than one robot to be transported, but also because they have a limited vision range, so they cannot see at the same time the object to be transported and the goal location. So they have to find a way to help each other to find a path to the goal location. So we have the robots, we have seen it in the video before, and now we need to write the controller, the software that controls the robots so that they can do this stuff. And to do so, we took what is known in robotics as behavior-based approach. Basically, the idea is that you identify a number of basic behaviors the robots have to have, and then you implement the basic behaviors, and then you implement an arbitration system between the behaviors. Okay? And the behaviors that we identified are set assembly, coordinated motion, cooperative transport, and goal search and path formation. So the names should already give you a hint of what they are intended to do. For example, self-assembly is a behavior that lets robots attach to each other. Right? And the way it was implemented is, well, in fact, the behavior itself was learned, but what the robots learned was that if they are red, this can be interpreted by the robots as a grasp me signal. If they're blue, this means stay away from me. Okay? So the robots have this camera that you see here that is pointing on the ceiling, and here there is a circular mirror, so that the robots basically has a 360 degrees vision around. So you can see the robots around, a rough idea of the distance. And so what they see is basically are blobs of blue and red light, and they try to move in the direction of the closest red light and then to grasp. Okay. Then another behavior is coordinated motion. Here, the problem is that if you touch together some robots with tracks, they have to coordinate the way they move, otherwise they get stuck. If a robot is pushing in that direction and one in this direction, they just don't move. And here you see how they're moving. This is an example of cooperative transport, where the robots basically are cooperating. They feel the force that each robot is exerting on the object that is being transported, and they use this force to coordinate their movement. So the way that the behaviors, this software for the different behaviors is developed has been done in two different ways. Either using a machine learning approach or by designing the software, the rules. Okay? In the case of the machine learning, the method used is quite simple. Basically, we use neural networks that are black boxes where you have some inputs and you get some outputs. And the problem with these neural networks is that to find the mapping between the input and the output is not that easy. And it is given by weights, by numbers that you add on these connections. Okay? So to find the value of these numbers for these connections, we have used a genetic algorithm. Basically what we do, without going into the technical details, is that we code these numbers that are the numbers that define the behavior of the neural network in a string. And we interpret one of these strings as an individual, as a chromosome. And then we create a population of these chromosomes. It means we have many neural networks. And these chromosomes are generated randomly. Then we apply things genetic algorithm that is kind of abstraction of what happens in population genetics, where we test each of these individuals, that is each of these neural networks on the robots. We measure how good they are at solving the task that they were giving the robot. And then we give a probability of reproduction to the next generation that is proportional to the quality of the solution they found. Then we apply also some things that are equivalent of mutations and crossover, and we produce a new generation of chromosomes. And we repeat this over and over until we get controllers that are good. So basically, this is what I just said. As I said, I don't go into the technical details. Basically, what we get is graphs from experimental graphs like this one. We have this generation number, and we have here the fitness, where the fitness is the quality of the solution produced. At each generation, we have 100 individuals. It means we have to run 100 experiments to evaluate the quality of the behavior. And in fact, we have to even run more because the algorithms are stochastic, so you want to reduce stochasticity by running the experiments. This means that to get this graph, you have to run something like 50,000 or 100,000 experiments, which is the reason why we do most of our experimentation in simulation, that we have built a simulator of the swarm that's allowed to simulate swarm robots quite efficiently. And then once we have found something that looks good, we test it on the real robots to check whether it is really working also on the real robot. So in this case, we have run these 50,000 experiments. We take the best individual, and then we put it on the real robot, and it manages to let these robots move in a coordinate. The same controller is on this robot that are attached to each other in a different way. Okay. So this is the typical approach to use the machine learning approach. Now, in some cases, we take directly, when it's possible, or when we have the inspiration, we take inspiration directly from some real swarm behavior. Gauss search and path formation is what we did. Basically, we wanted to mimic the ant wave formation that we observe in real ants or in termites. But the main problem is that our robots cannot neither deposit nor sense pheromones. So what we did was to create a system that is inspired, let's say. So basically, we are using robots instead of pheromones. The idea is the following. Well, let me first say that the robots can distinguish between 3 colors, up to 20, 30 centimeters, and they can say which color is closer. So I should add that they can make also a lot of errors. So these are not deterministic things. And the idea is the following. Let's say that the object is there, that the goal where you want to transport the object is here. So the object is red and the goal is blue. And robots start to move around in the environment, and when they see the blue, they start to move around the blue. And when they reach maximum distance from the blue that is given by their sensing capability, so basically these robots have a sensing basically like this, so it can see the blue up to this distance. So when it is here, it can, with a certain probability, decide to stop and become the first element of a virtual chain of robots. And if it does so, it takes a color that is a function of what the color that it was seeing. So if it sees blue, it comes green. And now the procedure continues. Now the robots turn around either the goal or this first element of the virtual chain. And again, when they reach maximum distance from either the goal or the first element, they can stop and become a new element of the chain. This could happen also here, and you could have more chains growing in different directions. And the procedure goes on this way. If a robot like this one is here and it does not see any other robots in its neighborhood, so the only one that it sees is this one, it can, with a certain probability, decide to give up. And if it decides to give up, the chain is destroyed and the robots become available again to search. So here, what I'm showing here is one particular chain that was successful, and now when the chain has reached the object, this chain is frozen and can be used by other robots to find a path to the object. Okay, this is a particularly simple case. You can elaborate on this. First thing, you can have many chains that go on no direction. Second, you can have a chain that starts also from the object, not only from the goal. Third, you can have chains that just walk the space. When the chain is frozen, it can be made linear. Okay, there are a number of optimizations that you can do on these, but I'm just explaining and showing the basic stuff. Okay, so now we have basically all the pieces in place to solve the basic search and retrieval problem. And so what you see here is a simulation where we have the goal location here and 4 different objects that can be retrieved. And you see the robots forming the chains and joining chains and leaving the chains. And now these chains find that object. So now other robots can use it. Since it has 3 colors, it has a directionality, so the robots can follow the chain and grasp the object and retrieve it. And so in the next video, I'll show you the experiments with the real robot. So here we have okay, so we have the goal location, the object to be transported. The object weight is such that it requires at least 3 robots to be moved. The vision field of the robots is approximately this distance. The robots are placed randomly in the environment. So what they do is they are switched on and they start to move kind of random way in the environment, and then they will start to build chains. So you see these chains have been built, and at some point the robot has given up. So there are chains that are built over and destroyed all the time. And at some point one chain happens to be built in this direction. What is important to note is that the robots, they really don't know what they're doing. So they're just applying rules. And even once this chain has been built, you see this robot is still trying to build the chain in that direction. So now these robots have formed the chain, and once they see the red light, they grasp it. Huh? And once they are free, they can transport comfortably the object. But still, their vision, you will see in a moment in another video, the vision is very noisy. So they can do stupid things, and you will see it in a moment. They move in completely to a wrong direction. But since the mechanism is quite robust, because once they, you see in a moment, okay, now they're moving away. Okay? So you see that the other robots just filling immediately so that the chain is built again and the robots manage to go back to the original behavior towards the goal. Okay, so I just want to show, before I talk about humanoid, I want to show something about more recent work. So the idea of a functional self-assembly. So to use this self-assembly capability as a response to something that happens in the environment. So the idea here, for example, is that the robot arrives here, the first robot arrives there, and sees that there is a gap. He cannot go over the gap alone, so he stops and he switches on his red light, and he calls for help, basically, so that other robots arrive, and they can, by attaching to each other, they can pass over the gap. So one of the experiments we've done is what you see here. So there is an environment where the robot starts, and there is a goal location, this side, and there is a hill in between. So you see the hill, in this case, the hill is low, and the robot managed to pass over the hill. But in another situation where the hill is higher, so it's much more steep, the robot does not manage to pass. In fact, you see that they are stupid because he continues to try until it happens. Okay? So the idea is that they have an accelerometer that can be used to feel the steepness. So the idea is that when they feel the steepness, they can just switch on a self-assembly behavior, which is first initiated by becoming blue, and then randomly one of the robots becomes red, which is the real seed for the self-assembly behavior. Then the three robots, in this case there are three robots, they attach to each other, and they manage to pass over the hill. Unfortunately, this type of solution is not very robust because you see in a moment you have three robots, they start the self-assembly. They self-assemble, but so we don't have, in this case, we don't have any control on the number of robots, not even on the morphology. So the situations in which it works and situations in which it doesn't. But this type of problems prompt us to study morphology formation and how to control the morphology of a robot, which is what you see in this short movie, which also show you how bad is the vision, so how much stochasticity is in the system. Can you?
In this video, we use the Swarmbot robotic platform to show how robots can autonomously form to specific morphologies. Each so-called S-bot is completely autonomous. The pattern formation mechanism that we design is completely distributed. That means that none of the S-bots have any global idea of the pattern that is being formed. The S-bot LED ring and camera allow S-bots to locate each other and provide a simple form of communication. As the S-bots connect to each other, they use simple rules based on what they can see around them to decide how to extend the pattern. This type of visual communication and navigation is, however, extremely limited because of the range of the camera and the limited processing power of the S-bot, which only allows for crude three-color segmentation. An S-bot can open what we call a connection slot by lighting up its blue and green LEDs. A connection slot indicates both the desired angle and the specific place in which a connecting S-bot should grasp. After each connection, both the grip and gripping S-bots change their configurations. These configuration changes follow simple rules based on what the S-bot can see in his immediate surroundings. By manipulating these simple rules, different morphologies can be formed. Each robot only acts on the basis of local information. None of the robots have any concept of a global morphology. Nonetheless, when many robots all follow the same specific set of rules, a distinct global morphology emerges. The morphology generation mechanism is generic and allows for an arbitrary number of different morphologies to be formed. To demonstrate the mechanism, we formed 4 different morphologies: the star morphology, the line morphology, the arrow morphology, and the dense morphology. We generated morphologies using up to 9 real autonomous robots. The morphology generation mechanism proved robust and reliable, with a connection success rate of over 90%. Because the morphology construction mechanism is distributed, it scales well. We have conducted scalability tests with larger numbers of robots in simulation. In ongoing research, we are currently extending this system so that the robots can adapt to different situations by autonomously choosing and constructing an appropriate morphology.
Okay, so once we have this capacity of controlling the morphology of the robot, then we can do more complicated things, like the experiment that I show you now. We have an environment in which robots start here, and they have to take 3 different morphologies depending on the type of situation in which they find themselves. For example, here there is a gap from here to here. Here there is a much bigger gap, but there are 2 cylinders, like a kind of bridge on which robots can pass. And here there is an inclined plane, and there is a ball that the robots should be able to push towards the goal location that is given by this light here. So the robot managed to, they have a number of predefined possible morphologies, and they managed to recognize the situation and to choose which morphology to use. So for example, you see here in this case, the robots use a linear morphologies that allow the swarm bots to pass over the gap. Here, the robots go hand by hand to pass over. Here you see that if they choose a wrong morphology, they cannot pass over the bridge. And finally, here we have the inclined plane, where here you see that using a shovel morphology, they manage to push the ball, but if they, for example, choose a linear morphology, they cannot. So these control on the morphology allows us not only to pass over the hill, but to solve a number of different problems where the shape of the swarm bot is important. Okay, so let me now tell you something about Swarmanoid. Swarmanoid is a second project, is a follow-up of SwarmBot, and the idea here was to move from the plane 2-dimension to 3-dimension, and from a homogeneous swarm to a heterogeneous swarm. So in this case, rather than having only robots that move on the ground, we also have robots that can climb objects and that can fly. And we give these 3 robots names that are reminiscent of their main capability. So N-bots are robots that can manipulate objects, Footbots are robots that can move on the ground, and I-bots are robots whose main function is to provide vision capabilities and are robots that can fly. So this is a handbot. So big, It has 2 grippers here. Each gripper has a camera so that you can see what is gripping. It has, the gripper can be used either to grasp object or to grasp structures, you will see in a video in a moment, where it can climb. The robot also has a ceiling attachment system, that you will see also in the video. Basically, it's capable of launching a rope to the ceiling so that it can use the rope as a help in climbing and descending structures. And it has fans that allow it to rotate when attached with the rope. So you see here, robot, these are the 2 grippers, these are the fans. And here is the robot climbing the truss. Then we have the footbots, which basically are better engineered versions, a little bit bigger than of the S-bots that you've seen in the previous project. They have approximately the same capabilities. The attaching mechanism has changed, I'll show you in a video. Their main function in the experiment is to transport around the handbot. The handbot cannot move on the ground, so they can only grasp object or climb. So if they want to be, they need to be someplace, they have to be transported by the footbot. And so you see here the footbot, they still have a ring around, and the grasping mechanism now is done in this way, so that it arrives against the other robots and opens and is grasped. And finally, we have the iBot, which is a flying robot. It has a ceiling attachment system here. Okay, in both cases, we have made the hypothesis, which is a simplification, to have a ferromagnetic ceiling. It means that this is here an electromagnet, and the robot can use it to attach to the ceiling. And this is necessary because these robots here, they can fly for a few minutes, and after that the battery is off. So if they want to collaborate with the rest of the swarm, they have to be able to leave, to act longer. And this is done by letting them shut down their motors once they have reached the location where they have to be. This robot has, as main capabilities, has a camera that points towards the ground that can be used to recognize robots or objects. It has lights that can be used to indicate a path to the robots on the ground. And it has also some infrared communication. And you see, okay, so it was flying, and now it's attached to the ceiling, and just stop the robots. And also in this case, the type of task that we are considering is a search and retrieval, but this time the object to be retrieved is placed somewhere on a shelf. And the robots have 3 types, as I said, and they have to collaborate to find this object to retrieve it. And the way it works is that we have robots, flying robots, that are here in the simulation of these red discs that explore the environment, and they build basically a path in a similar way to what was done previously with the robots on the ground, using their lights. And the robots on the ground, well, the footbot grasp the handbot, and they try to transport the handbot to the location where the object to be retrieved is, and they are guided in doing so by the robots on the floor, on the ceiling, sorry. So the robots here, the iBot are exploring, and once they have found the object, that is a book on that shelf there, they switch on their lights that are used by the robots on the ground to find their path. Okay, so you see in a moment. Okay, now they've found the book, they switch on. Here there are arrows, in reality are lights, you'll see in a moment in the real video. And the robots on the ground, the footbot transport the endbot. They transport the endbot to the structure. And when they reach the structure, the endbot climbs the structure, retrieves the book, and then is taken back home. So, next, I show you a short 5-minute video that is Swarmanoid the movie that presents this experiment in detail.
Swarmanoid is a heterogeneous robotic swarm made up of 3 types of robots. The handbot is designed to manipulate objects. The handbot can also climb, but needs help from other robots to move around. The footbot is a wheeled robot with a gripper. Using its gripper, a footbot can form physical connections with other footbots or with a handbot. The iBot can fly and rapidly explore large areas. It can attach to the ceiling and provide environmental information to the other robots. In this film, the Swarmanoid is deployed to find and then retrieve a book. Here, the Swarmanoid has already partially explored its environment. As the iBots search, successive iBots attach to the ceiling, forming a connected network. Once an iBot has found the book, the knowledge propagates back to the deployment area. The handbot then requests transport assistance from the footbots. Using the iBot network, the footbots form a ground-based chain linking the deployment area to the book. The composite footbot-handbot entity then follows this ground-based chain. A second handbot prepares for transport. The first footbot-handbot entity has rotated and aligns with the bookshelf. While climbing, the handbot supports its weight with the cord attached to the ceiling.
So you can imagine we have broken many of these.
Actuated fans give the handbot control over its angular rotation around the vertical axis. Humanoid is a parallel distributed system. Parallel activity and redundancy increase its robustness and flexibility. The second footbot handbot could retrieve another foot, or act as a backup should the first footbot handbot fail. In this film, the swarm retrieves a single book. However, the true value of the swarmoid concept would manifest itself in parallel task execution scenarios and in unstructured environments. Future incarnations of the swarmoid might be able to replace human workers in hazardous environments, perform search and rescue missions, or even conduct exoplanetary exploration.
Okay, so now the last thing that I want to show you is some very recent work that we're doing again to try to put together the use of flying robots and the morphogenesis capabilities of our robots so that the flying robots can help the robots on the ground choosing the right morphology when the robots on the ground don't have vision enough of the environment. Well, I just show you the video. It's a short one. So it's about the cooperation between Footbot and iBot.
Some tasks are just too difficult for the robots to solve on their own. So-called self-assembling robots can combine forces by connecting to each other in a broad range of morphologies. But it's hard for the robots to know when to use different morphologies because of their limited local sensing range. The solution? Flying robots. Flying robots can analyse the environment to see what task needs to be solved, what morphology is most appropriate to solve that task, and which robots are best placed to perform the morphology. However, it is non-trivial for the flying robot to communicate with specific robots on the ground. The problem is that the robots are very different parts of the world, which makes it difficult for them to agree on a common frame of reference. We have developed a method that allows robots to select their communication partners without relying on any kind of global coordinate system. We refer to our method as spatially targeted communication. Let's say a flying robot wants to communicate with a specific robot on the ground. This one, for instance. To start the selection process, the flying robot illuminates its red LED. To join the selection process, the robots on the ground light up in blue. In a series of elimination steps, each ground-based robot independently displays a sequence of randomly selected colours. At each step, the flying robot matches the colour of the target robot. Whenever a robot on the ground sees that its own colour doesn't match the flying robot's colour, it eliminates itself. The process continues until only the targeted robot is left. An extended version of this method allows adjacent groups of robots to be selected and then given movement and morphology formation instructions. Here, the flying robot has already targeted the 4 robots closest to the hill and instructed them to form a line morphology. Spatially targeted communication expands the potential of self-assembling systems by allowing ground-based robots to benefit from cooperation with flying robots. Any robotic platform equipped with LEDs and a standard camera can participate in spatially targeted communication. Our current focus is on bringing our research out of the laboratory and into the real world.
Okay, so I'll just let you know that there is an international conference about the subjects from intelligence, but and then there are web pages where you can get the movies and information, articles, and so on. Okay, thank you.
some question or curiosity?
Yep.
Yes.
What kind of features are you developing the Swarm so?
Okay, so it's kind of difficult question because we are far from real-world applications. You can imagine what I was mentioning in one of the videos, search and rescue is a possible application. We are starting to work on swarm construction, having swarm robots collaborate to construct some structures. These can be particularly interesting for creating habitats. We are preparing a proposal for another project for a swarm of submarine robots that should be used to as a aid in repairing the coral reef. But I think really that real-world application will need the robots that are more performing. So the robots that we have, as you have seen, are very brittle. They are not very, when you compare to any kind of animals, they are much, much less capable. So having them to move around in the real environment, they break down, they don't have enough power. So there are big hardware limitations that makes it difficult for the moment to predict where, because it depends, probably depends more on the development in robotics than in swarm robotics.
I was a bit, what it seems a bit peculiar as research is that the complexification seems to stay on the side of the robot rather than going on the environment. Maybe it's because we are now in a scalable architecture, but what if we have a swarm of dunes? The obstacle for the robot remain one. And for me, that is, I don't have a super clear question, but for me, that is a little bit problematic in a way. No? The robot deals with a single book. So the environment around the robot is kind of very simple. And somehow I think it would be interesting to run a set of experiments where the robot maybe fails as well, but deal with the articulation of the environment.
Yeah, I completely agree. But if you were trying to do these experiments, you would realize that I would say it's nearly incredible that you managed to do this with one single group in that specific environment. If you, as soon as you start to make the environment more realistic, let's say, and less engineered, robots can start to fail. There is no way that you. This is why I'm saying that it's probably the future of the application is more in the capacity of in the hardware, in the robots, than in the research in robotics. Because at the end, the research in robotics is how to coordinate the agents. And then if you have agents that are very flexible, that they can walk on grounds that is not flat.
Maybe the environment can be engineered, but engineered in a different way. What I'm thinking is, if you think about a city, you have a series of swarm systems, but you also have a resistant set of very static elements that could be abstract as a system of static elements. It's not to throw the robot in the real city, but maybe to abstract the environment of the city as a that is for the interest of my research. But one interesting research would be to try and confront a swarm of robot with a swarm of objects that somehow are an engineered abstract version of an environment, but they are not a hyper-simplified environment of one single object. I don't know if you are following.
Well, we have other experiments I have not presented in which we have many objects to be retrieved or many objects to form clusters, or we have even active objects that can represent abstraction of tasks that go a little bit more in your direction.
I was, there are many elements that really I found really intriguing. It's super interesting research. In particular, of course, probably relates more directly to our work. There is these aspects of morphologies, no? So how you are able to give robots the ability to organize themselves into different morphologies, into different patterns. And I was thinking that obviously that is very interesting because, you know, from my point of view, it's about talking of morphology as something that is emergent, that is self-organized, and is not necessarily kind of described or depicted geometrically how we are used to doing normally as architects. But then on the other hand, it made me think about something which relates back to a video that you show at the beginning, where the ants themselves, for instance, creates these bridges or creates this connection, and which in fact are kind of morphologies, emergent morphologies. And it made me think it would be interesting, perhaps in that sense, to work with robots that maybe are even more simple than the one that you are designing, even like cheaper or even easier to build, but actually where you have lots of them. And maybe in that sense, the morphologies that can be, can emerge, can go even further away from, let's say, the simple geometrical variations that you can achieve with NAND. And as you were mentioning before, maybe also can be less precise in terms of geometry, no? But more kind of closer to that model that we were looking at the beginning. I don't know if that's something that you are also thinking of, or
it's
maybe
the direction in which we are trying to go. Simpler robots, more specialized on some specific aspect that allow to do something very well, but only that. And the robots are, this is the direction we are trying to go.
So,
because the problem with these robots that we have seen is that they still require a lot of engineering.
they're still very
even if they're simple, they're still quite complex. Yeah, the problem is when you design a robot like this, you leave you the possibility to do something different from what you thought at the beginning. So it leaves you some flexibility. If you go the other direction, you design a robot, if it does not work for what you were designing, you have to start over. Okay? So it's a different way of thinking. You have to design the robot and the experiment at the same time and be prepared to throw everything away if it doesn't work. So it's not the way that roboticists work usually.
But on the other hand, if you can make robots that cost $1 each to make, and you can have a bunch of architectural students producing 1,000 of them in 1 month, suddenly
Yeah, sure.
you can try. I'm just thinking.
There are some efforts in this direction. For example, there is a very simple robot called a Kilobot that is just doing very simple things. It's very cheap, and so we have 100 of them in the lab. But then finding that robot was already built. Okay, so finding the right experiment becomes very complicated. So the right way to go would be to have the idea of the experiment that it looks interesting, and how the robot should be done, and design the robot. I mean, do all the things at the same time.
Yeah.
Typically, these are there are different expertise because of these processes that belong to different people. So, and those that build robot do not reason in that way that you propose, which I think is very interesting. So it's difficult to find a roboticist that will work with you along those lines. Basically. So we have to do it in-house.
Sure.
Which is difficult because we do not build robots as a profession. As I told you before, there is a very nice example in the direction that you're saying in an article that just came out last week in Science. That is done there's work done in hardware, where the robots are really simple and they do, in an interesting way, a construction task. But there are not many examples.
Okay.
As you said, one of the challenges of this is battery power. How it doesn't last that long with the iPods. So are you looking at ways that they could self-charge, or maybe they could, recognize the need for charging?
Okay, the easiest answer is it is not my job. There are researchers whose goal is to find better ways of giving autonomy to robots. Now, for the specific of our robots, the new ones, they have hot swappable batteries, which means that you can remove a battery and put another one without, and the robot can stay, I think, 10 or 12 seconds on without battery. And we have an automatic recharging station, which means the robots can go in this station, they recognize the station, and they can hot swap the battery. But it's just a practical solution, it's not.
But there's no like a contact plate where they just go onto them and they can just charge. It has to be someone swap.
Yeah, because if you want to recharge, then the robot has to wait 1 or 2 hours to recharge. So basically, there are solutions, but are always solutions that are very ad hoc, because it is not the goal of this type of research to solve that type of problem. Okay. So, for example, there are robots that have contacts on the below them, and they can move on a carpet, electronic carpet that's been built on purpose, so they basically recharge, or they use the power from the carpet. Obviously, as an ad hoc solution, which is not something that you can think that is viable for real-world application. But it allows you to run experiments for hours and hours without taking care of recharging the robot.
Are there research on PV panel or these kind of things attached to robots, or like simulation? Because there are some toys that are like that, but I don't know if there is any.
Now there is also the possibility to recharge by induction. As I say, that it's really not.
Okay.
Yeah, it's not my research.
More questions?
Yeah.
Well, is that me or someone else?
I don't know.
You can go.
Bye-bye.
Okay, I'll make a very simple question so to understand myself. You use a lot of the word optimization, and I would like to kind of understand what's the shift to the paradigm in the idea of the optimization, because you mentioned a lot that it's not that it is the optimal, but it's the good enough or the satisfying one. So why this kind of approach is being evaluated as better than kind of the previous paradigm,
So
or the single
this
robot?
There's nothing to do with the robotics. Huh?
Yes.
Is the previous part.
Mm-hmm.
Yeah. So the idea is the following. We know since the 60s that there is a large class of problems, which is the problems that are known as NPR, or NP-complete, whose complexity grows as more than polynomially with the dimension of the problem. Which means that you might have an algorithm that solves to optimality the problem of allocating, 100 activities to 100 locations in an optimal way. But the same algorithm cannot solve the problem with 101 activities in a reasonable amount of time. So for these problems, so finding the optimal solutions, most of the times it's not feasible. So what has been proposed is that you can find good solutions with stochastic algorithms. A stochastic algorithm in general do not prove, you cannot prove convergence to the optimal solution in finite time. You can always prove convergence to the optimal solution in infinite time, which is good for a mathematician. From a practical point of view, who cares? So this is the change. You do not think anymore of finding the optimal solution, of searching for algorithms that find the optimal solution, but you search for algorithms that find good solution fast.
No, thank you, because I think it's kind of, first of all, we try to think this kind of new system implemented into the real world, which for us the real world is kind of the city. It's kind of interesting to understand that for what reason we going through this kind of research, through this kind of thinking, to kind of propose or to speculate about new systems that can actually substitute, to replace, or if you like, to enhance the existing.
If you want to, I don't know, set up a system in a city where you have a kind of taxi service, well, not taxis, but bigger, serve more people, and you want to do this dial-a-ride system, okay? And you want to find the optimal way of allocating costs to drivers. This is a problem that you cannot solve optimally. Okay? There's no way. So the research in the stochastic algorithm is about finding solutions to this problem that are good, are not optimal. Maybe they are 10% more optimal, maybe 1%. But the important point is that they are fast, so that you can use them.
Good.
I have another one question,
Yeah,
a bit technical one this time. We'll be able to, because you run all the evolutionary techniques in the computer before you actually find a behavior that is satisfying. Would it be possible to, I mean, can you see in the near future to have this kind of real-time evaluation? I mean, it's
On the real robot.
on the real robot. So the real robot actually can evaluate itself in a local and a global level at the same time. A kind of.
No, I think that given the technology, having the evolution on the robots is not feasible. Having mechanisms that allow the robots to have some ideas of how well they're performing, yes. There are other approaches like reinforcement learning that are also allow robots to learn something. But usually they learn the values of parameters or not the whole behavior. Maybe it's a question of the efficiency of the algorithm and the time it takes to run the simulations or the real robots experiment. Even if the robots had no autonomy problem, still it would take a huge amount of time. Which is also something that is related to the culture of research in a given field, because I mean, when there are ethologists that make research on animals, they have to do the experiments with the animals. There is no other way. So they can take years. And this is accepted because there is no other way. In robotics, people working in robotics, they are also computer scientists, and they know that by running simulation, they can get the results much faster. So why to spend 10 years' time on PhD students if you can do the same in 1 week?
Any more?
Can I ask a question? You have mentioned some ideas about self-organization and local values, but in your last exercise, it seems that you are trying to introduce a iRobot, right? iRobot as an observer, and it's trying to extract the information from the global value and then give a feedback to the your local agent or local unit to tell them which one is the best morphology, right? So how could you explain
So there is
this
a,
to the
in which
self-organization?
one? In the very last video
Yeah.
or in the Swarm line?
So the very last video,
Very last.
they're using the, yeah.
Yeah,
He's
that-
returning your
Yeah.
critique on his webcam. Something.
Because it's trying to use an observer or maybe a camera or something. You're trying to extract the information from a global point of view and then give the feedback to a local. Yeah.
It's true.
It's true. So
we try many things, and this one
yeah,
was
but
on that. We tried.
how to explain it if you really want to use the self-organization or just using the local.
But if you wanted to do the robots to do the self-organization alone, they have to try fail, as we did in the other experiment that I've shown before, where the robots have a certain number of possible choices, and they arrive and they try. There's no other way.
So basically, the iRobot in that sense is kind of helping them to coordinate faster and
Yeah,
more
yeah.
effectively. Is this also
It's
related to
almost-
the
it's
number of
almost-
robots on the ground, or I mean, if there were like 100 of your wheel robots, maybe it would be different, or that is actually two independent.
No, in that particular case, the number of robots on the ground, well, it has to be able to see all of them.
Mhm.
Okay, so there's for sure a number that is too big, but it doesn't change the behavior. The question on the self-organization is, okay, so it depends on, if you look at the robots on the ground as a whole, the robots flying as a swarm, then there is a problem, because there is a robot that, if you look at the robots on the ground and the robots flying as a swarm, heterogeneous, then the problem disappears.
Right.
Because there is one robot that is looking from the above, but is part of the swarm. If it is not that one, it's another one.
Okay.
So it's a,
Is this a conceptual level or also the kind of programming level you think?
a conceptual level.
Okay.
It really depends on where you, how you define the swarm and what are the elements of the swarm. In a swarm, you can have all the elements that are equal, the same, or it could be each element different from the other. So, I'm trying to think online. If you have these flying robots, and they are part of a heterogeneous swarm, then the fact that a flying robot is telling to those on the ground what to do does not imply any philosophical problem,
Yeah.
because they are still part of the swarm.
I mean, ants are an heterogeneous swarm in any way, no? Like, because they have different tasks, different things. So.
Yeah, it's true that the difference in capabilities between the workers and the soldiers are not as big as a robot that is on the ground and not
Yeah,
on the
that
ground.
seems a bit big to me as well.
It's a bit
At the
maybe
moment.
like a question of design, maybe also. Because it takes a conceptual effort to consider them as part of the swarm, in the sense that when you look at them or when you see how they behave and what they do, they
They
kind of
seem,
really look like different typologies.
Maybe they could be
Yeah, but from the
gradient.
point of view of programming and communication, I mean, obviously what we see is the physical aspect. The physical aspect is very different. But from the point of view of the behaviors and communication capabilities and so on, they are much more homogeneous than what it looks like.
I think this raises a really interesting thing architecturally
Yeah, no?
in some way. You know, and I think this is something that, at least I know, that from a design point of view, enables you to think about form as actually being different kinds of behaviors, and raises a question that you guys can think about your design projects, that architecturally and spatially things can perform different ways, different ways with simple rules, but still be part of the global sort of arrangement of the global assemblage as well. Because that's somehow where the architectural translation comes in.
Yeah,
And I think that's really
I
interesting.
think for us as a designer to see them so formally different, and even though you say that they are part of the same world, swarm, and algorithmically they have a sort of relationship or is very similar, for us is kind of strange because our research is really in associating, the morphologies to the behavior and consider them intrinsically related. And
Yeah, but I mean, to me too, is
Okay.
when I look at that, and I have always the feeling that if I say it is a heterogeneous swarm, I'm a little bit forcing. But in reality, if I look at the logics, they are a heterogeneous swarm, and the heterogeneity is given only by the physical.
yeah,
I mean, I think it's interesting the fact that, like, because actually I think the idea that when you think about the swarm, you think about elements that are like large number but all the same. I think that's also a little bit of a simplification. I mean, in a way, it's kind of interesting, the idea of a heterogeneous swarm, because in fact, I mean, there's no reason why they have to be all the same.
yeah,
But
it
maybe
would
the
be
articulation of
interesting.
difference is interesting.
Also in the discussion of the morphology before, like if the morphology can be a little bit more complex, if the ground one get attached to the flying one, if they are more similar component, and at a certain point, maybe not now, but while you run the experiment, you start to think about way they can physically have relationship, not only virtually.
Yeah.
But and then they act more as a swarm because they have a physical and virtual relationship now. And if they have physical and similarity, even though they might have some difference because one fly and will have for sure, and the other might have some clumps. But if they have more, then maybe they have more possibility to have also physical relationship and therefore have on maybe more complex morphology.
Yeah,
as you were saying
but
before.
it was one of the goals of the project at the beginning, when I wrote the proposal, to have much more physical interaction between the companies. And then it didn't work out.
Okay. Other questions?
That's it? More? No? Gina, nothing.
I actually have a question. Mark, I've got a question.
No.
Now,
For me later. It's rude. I mean, he's our guest. I mean, you should direct questions.
Okay, I'll ask Dr. Wieringa. I mean, how would you apply these perceived complex morphologies which you develop through your robots to an urban environment? And how would that visually look like, and what would it actually give us, human race, to benefit from?
I think that I'm allowed to say I don't know. Well, I can try to answer this question next year after 1 year thinking.
You will think just about your question for 1 year and then we'll invite him back and see how it goes. Thanks a lot.
Right.